motion of planets, moon, sun, etc. puzzled many scientists. It was Ptolemy in the 2nd century AD who put forward a theory known as geocentric theory. According to this theory, Earth is the center of the universe. All other planets, including Sun, revolves around the Earth. This theory is also known as Ptolemaic theory. And geocentric theory was accepted until Copernicus. Copernicus, a Polish monk, proposed a theory known as heliocentric theory. According to heliocentric theory, Earth along with other planets revolves around the Sun in a circular orbit. And this theory was accepted for many years. And then Kepler, an assistant of Tycho Brahe, who analyzed the observations of Brahe and supported the heliocentric theory and put forward as a result in the form of laws called as Kepler's laws. At present, all physicists follow these laws related to planetary motion. The first law of Kepler, this law is also known as law of orbits. First law of Kepler states that all planets revolve around the Sun in an elliptical orbit of different radii, with the Sun at one of their foci points. Already you know that what is an ellipse, and you know ellipse is having two axes. This longer axis is called major axis and the shorter axis is called minor axis. And these 2 points, F1 and F2, these are called two foci. According to Kepler's first law, a planet revolves around the Sun in this orbit so that Sun is one of its foci. When planet is moving around the Sun, at some point it is nearer, at some point it is far away. But throughout this orbit, the angular momentum is constant. And using this principle, you can expect what are the velocities at different points. Yes, when it is nearer, the velocity is somewhat more compared to when it is away from the Sun. Consider the system of Sun and planet, due to which force the planet is moving around the Sun. Yes, due to gravitational force between planet and Sun. It is a mutual interaction between Sun and planet. Is there any external forces acting on the system? No. Is there any external torque is acting on the system? No. Since there is no external torque is acting on the system, the angular momentum of the system remains constant. Already we know that if external torque is 0, the angular momentum remains constant. In this case, the angular momentum is constant. And this distance, when the planet is nearer, it is called perihelion, and the distance when it is away from the Sun is called aphelion. Periheli and apheli. In general, the distance between Sun and the planet is taken as the average of these two. Now we go for second law of Kepler. According to this law, an imaginary line drawn from Sun to planet, which is also called radius vector, sweeps out equal areas and equal intervals of time. Suppose you consider a planet is moving around the Sun, as I was saying in the figure. Let A and B are two positions of the planet for a period of 1 month. C and D are also two positions related to time interval 1 month. The line joining Sun and planet sweeps some area at this position. If you compare these two areas are equal. This is Kepler's second law. Suppose if I consider 12 equal intervals of a year, that is 12 months, the area swept during these 12 months are equal. That is, the Kepler second law is imaginary line drawn from the Sun to the planet, that is radius vector, sweeps equal areas and equal intervals of time. This law is also called as laws of areas. Next we go for third law of Kepler. According to Kepler's third law, the cube of the average distance of the planet from the Sun varies as the square of the period of its revolution. That is t square proportional to d cube. Already we know that the length of the line drawn from Sun to planet is not constant. It is not same in an elliptical orbit. Therefore, the distance between planet and Sun is taken as mean or average distance of these two positions. If t is the time period of revolution of the planet and d is the average distance of the planet from the Sun, then Kepler's third law is t square proportional to d cube. If t1 and t2 are period of revolutions of two planets, d1 and d2 are the mean distances of the planets from the Sun, then according to Kepler's third law, t1 square by t2 square, this is equal to d1 cube by d2 cube. This law is also called as a law of time periods. And now we discuss some principles related to orbiting of a satellite. Already we know that when an object is dropped, it reaches the Earth along the vertical line in the absence of air resistance. Similarly, if the object is thrown horizontally with some initial velocity, it takes a curved path, but still it reaches the Earth. Now from this height, we go on increase the initial velocity. Then what happens? The range will increase. Thus, the initial velocity increases, greater is the radius of the curved path. If the object is given an initial horizontal velocity such that the radius of this curved path is equal to or greater than the radius of the Earth, then what happens? Now this is the curved path. Can it return to Earth? No, it will not return to Earth. For this path it can reach, for this path it can reach, for this range it can reach. If the range is more than the radius of the Earth, then this object cannot return to Earth. Now this object becomes an artificial satellite. It orbits around the Earth and the object becomes an artificial satellite. This is the principle we use in launching the satellite. When this object is moving around a planet, for what velocity the object will orbit around the Earth. In general, satellites are taken to required height and are given a required horizontal velocity such that it revolves around the planet. This horizontal velocity with which the satellite revolves around the planet is called orbital velocity. Now we are going to derive an expression for an orbital velocity. Suppose we consider a satellite moving around a planet. When it is moving around a planet in a circular path, do you know which kind of forces are acting on it? Yes, one is the force towards the center of the Earth. This is centripetal force, and this is the force required for the satellite to move around the Earth. The centripetal force required for the satellite provided by gravitational force of attraction between the satellite and planet. And due to the motion of this object along the circular path, and another force is acting, which is pseudo force, which is called centrifugal force. The orbit is stationary means centripetal and centrifugal forces acting on the object are same. Now in this case, the centripetal force, this is equal to gravitational force between satellite and planet. If we consider the object is moving with velocity v0, this v0 is orbital velocity, then centripetal force is mv0 square by r. This is equal to gravitational force between satellite and planet, which is g/mm by r square. Here small m is the mass of the satellite, v0 is the orbital velocity, capital M is the mass of the planet, r is the distance of the object or satellite from the center of the Earth, capital G is universal gravitational constant. From this we can write v0 square equal to gm by r. But what is r? If capital R is the radius of the planet, h is the height of the satellite from the surface, then we can write small r equal to r plus h. Therefore, v0 equal to root of gm by r plus h. If h is very less compared to capital R, that is, if the height is very less compared to the radius of the planet, then this can be written as v0 equal to root of gm by r. Already we know that the acceleration due to gravity on a planet, small g equal to gm by r square. Therefore, v0 equal to root of g into r. This is the orbital velocity. Now, one thing we have to observe, the orbital velocity is independent of mass of the object. If the planet is Earth, the orbital velocity for a satellite which is moving nearer to Earth's surface is 7.9 km per second. This we get by substituting the value of small g 9.8 meter per second square and capital R, that is the radius of Earth, 6400 kilometers. Escape velocity. We know that when an object is thrown up, what happens? Again it returns to Earth. If you throw with larger velocity, again it returns to Earth, but it reaches more height compared to previous one. I want to throw this object so that it never return to Earth again. Then what may be the condition? For this you think, why this object is not able to escape from the Earth's surface? Yes, some energy binds this object towards the Earth. Or we can say, at this position, because of some potential energy, this object is having some potential energy. Due to that, it bound to Earth. If you throw with more energy, more than this potential energy, then it can escape from it. You are throwing means you are giving some kinetic energy. If this kinetic energy is more than the potential energy with which it is attached to the Earth, then what happens? Yes, it can escape. That means if you throw this object with some velocity so that the kinetic energy can overcome potential energy, then the object can escape from Earth's surface. And that velocity is called escape velocity. That is, escape velocity is the minimum velocity required for a satellite or for any object to escape from Earth's surface from the gravitational pull. In this case, to escape from Earth's gravitational pull, work has to be done against gravitational force, and the work done appears as kinetic energy of the satellite. That means the kinetic energy of this object should equal to work done against the gravitational force, or the magnitude of potential energy with which it is bound to Earth. Here we can write half mv square. If ve is the velocity required, that is escape velocity, the kinetic energy is half mve square. This is equal to g capital M small m by r. This is the gravitational potential energy or work done against gravitational force. Work done against gravitational force is nothing but gmm by r square into r. This is equal to gmm by r. Now from this we can write ve equal to root of 2gm by capital R. Already we know that the acceleration due to gravity small g equal to gm by r square. Therefore, ve equal to root of 2 into g into capital R, where small g is the acceleration due to gravity, r is the radius of the planet. In case of Earth, small g is 9.8 meter per second square and the radius is 6400 kilometers. Therefore, the escape velocity is 11.2 kilometer per second. That means if you can throw an object with a velocity 11.2 kilometer per second, it never returned to Earth. This velocity, the minimum velocity to escape from Earth's gravitational pull, is called escape velocity. What is the relation between orbital velocity and escape velocity? Orbital velocity is v naught equal to root gr. Escape velocity is v equal to root of 2gr. From these two equations we can write the escape velocity v equal to root 2 into v naught, or v naught equal to 1 by root 2 into ve. This is the relation between escape velocity and orbital velocity. We take some problems related to Kepler's law. You say this example. The time taken by Mars is 1.88 years to go round the Sun. Find the ratio of average distance between the Mars and Sun to that between Earth and the Sun. What is given in our problem is Mars takes 1.88 years to go round the Sun. How much time Earth takes? Yes, it is 1 year. We are asked to find what is the ratio of distances between Sun to Mars and Sun to Earth. Already we know that t square proportional to d cube according to Kepler's third law, where t is the time period of revolution of the planet, d is the average distance between Sun and planet. From Kepler's third law, we can write T1 square by T2 square equal to D1 cube by D2 cube. Here T1 and T2 are the time periods of Mars and Earth respectively. T1 is 1.88 years and T2 is 1 year. Therefore, T1 square by T2 square is 1.88 whole square by 1 square. This is equal to D1 cube by D2 cube. From this we can write D1 by D2 whole cube equal to 3.534 by 1 and D1 by D2 is 1.52. The ratio of average distances between Mars and Sun and Earth and Sun is 1.52. Now we take another problem. What is the acceleration due to gravity on the top of Mount Everest, whose height is 8,848 meters, if the acceleration due to gravity on the surface of Earth is 9.8 meter per second square and the radius of Earth is 6,400 kilometers. Already we know that the acceleration due to gravity at some height, this is given by g prime equal to g divided by 1 plus h by r whole square, where g prime is the acceleration due to gravity at that height, g is acceleration due to gravity on the surface of the Earth, h is the height and r is the radius of the Earth. Now in this case, we are asked to find what is the acceleration due to gravity at a height 8,848 meters. If we compare the value of h with the radius of the Earth, the value of h is 8,848 meters, that is 8.848 kilometers, and the radius of Earth is 6,400 kilometers. Since h is very small compared to r, 1 plus h square by r square to the power of minus 1 by 2 can be written as 1 minus 2h by r using binomial theorem, neglecting the higher powers. Therefore, the acceleration due to gravity at height h, g prime is g into 1 minus 2h by r, and this is valid when h is small. Now substituting the values of h, r and g. In our problem it is given g is 9.8 meter per second square, h is 8,848 meter or 8.848 kilometer, r is 6,400 kilometer. Now g prime equal to 9.8 into 1 minus 2 into 8.848 into 10 power 3 divided by 6,400 into 10 power 3. Converting kilometer into meter, 1 kilometer is 10 power 3 meters. Now from this g prime equal to 9.8 into 1 minus 0.0028, this is equal to 9.8 into 0.9972. We get g prime equal to 9.77 meter per second square. This is the value of acceleration due to gravity on Mount Everest. We go for another problem. A satellite is to revolve around the Earth in an orbit of 8,000 km. With what speed should the satellite be projected into the orbit? What will be its time period? In this problem, we are asked to find what is the speed of the satellite to move around the Earth at a height 8,000 km. And also we have to find the time period of the satellite. For a satellite to move around the Earth, to maintain a constant orbit, the velocity required is nothing but the orbital velocity, and it is given by root of gm by r plus h. This also can be written as root of gr square by r plus h, where capital R is the radius of the Earth, h is height of the satellite from the surface of the Earth, and small g is the acceleration due to gravity, and capital G is universal gravitational constant. In this case, the radius of the orbit of the satellite is small r plus h, that is 6,400 km plus 8,000 km. Here capital R is the radius of the Earth, that is 6,400 km, and small h is the height of the satellite from the surface of the Earth. This is 14,400 km. On substituting the values, we get the orbital velocity v0 equal to square root of 6.4 into 10 power 6 whole square into 9.8 by 14.4 into 10 power 6. On simplification, we get This is equal to 6.4 into 10 power 6 into root of 0.68 into 10 power minus 6. This is equal to 6.4 into 10 power 3 into 0.825. Now this is equal to 5.28 into 10 power 3 meters per second or 5.28 kilometers per second. The time period of the satellite is t equal to 2 pi r by v naught. 2 into pi into r is the distance of the satellite from the center of the earth. It is 14,400 into 10 power 3 divided by the orbital velocity is 5,280 meters per second. On simplification, we get this is equal to 17,127.3 seconds. In minutes, to convert into minutes, just to divide with 60. Now this is equal to 285.5 minutes. The same answer in hours is 4.76 hours.